Talk today will be given by Julian Plavnik from Indiana University of Bloomington, and her title will be Semisimplification of contragredient algebras.
Thank you so much. Thank you, the organizers, for putting this together, and thank you for staying for the last talk. Probably many people started from traveling. So today I will tell you about semi-simplification of contragredient Lie algebras, and the idea is to talk about Lie algebras in some symmetric tensor categories. So when I saw the title of the conference, I thought, okay, instead of quantum structures in Lie algebra, I will do Lie algebras in some quantum objects. That was my idea. So this will be based on joint work. There are 2 papers on arXiv with Ivan Angiono and Guillermo Sanmarco. We're actually specialists in Nichols algebras and has a lot of Lie algebraic flavor. So my idea for the talk is to tell you about Lie algebras in the Verlinde categories, which are some important symmetric categories in positive characteristic that have been heavily studied in the last couple of years. So yeah, that's the idea. So we want to construct Lie algebras in Verlinde categories in positive characteristic, and how we will do it is, or we will obtain it as semi-simplification of contragredient Lie algebra in characteristic, and we will do it with respect to the joint action by one of the Chevalier generators that already appear in some of the other talks. The idea is that this construction is nice because in this case, we can get also a root system. We also have some lattice grading in this case of these Lie algebras. And we can define some non-degenerate invariant form that behaves well with the lattice grading. Sorry. So also one of the applications is that in this way, you can get new examples of Lie algebras in these categories. And I will tell you a little bit why we want this. So maybe let me tell you about symmetric tensor categories first. So the main character of the talk will be this Verlinde category, so I want to tell you about that. But for that, I wanted to just recall an example that it's more familiar. I always will be working over an algebraically closed field, but the characteristic will depend and usually will be positive later in the talk, okay? But first, we will work with a group G and we will look at finite dimensional vector spaces, or maybe representations of G, or we can think of K modules of G modules of finite dimension. I want finite dimension, and that's why I want to mention this category so we can keep an idea on what kind of things I'm interested in. So what are the good things that I see in this category? Okay, we have that it's K-linear and abelian, so we have, we have underlying vector spaces here, so we're fine. We have things, but in particular, I like that the home spaces are vector spaces and that I have exact sequences in this category, basically, right? But what I want to say, because I mentioned already tensor, is that different people think of tensor categories in a different way. So I want to let you know what I'm thinking when I'm thinking on tensor categories. So I will want first to have a monoidal structure. So I want my category to have a tensor product, an associativity, a unit. For that satisfies some axioms, right? Some compatibility axioms. Yeah. But what, in my case, I care about, and that's why here I'm asking about this finite dimensionality, is the existence of duals in my category, okay? So duals in the category here, I didn't say, I was talking in general at the end, but the idea was, okay, we have the diagonal axiom for for the group case, so we can act diagonally. And we have the contragradient action in the dual, right? So if I take the linear dual of some B, here we have a B, and I'm thinking of it just as a module because it's easier for the notation for me. So now I can endow my dual with a structure of a module again, right? So if T is individual, I will act here using this contragradient action, meaning that I will act with the inverse of the element in B, and then I will apply my function, right? Another nice thing about this category is that this category, the tensor product in this category is symmetric. So that means that the flip of vector spaces is a morphism in this category, is in this category, right? So maybe I don't need to write that. But that's what I will be thinking in general when I talk about symmetric tensor category. So I will ask always for the K-linear abelian structure, something that I didn't say here because I started speaking in general. So here I said that I want to have the tensor product of two modules to be again a module, but I mentioned that I need to have a unit, and here the unit is the field with the trivial action. I mix between the specific example that I wanted to use as the example, but sorry. But K-linear abelian, the first thing. Then I want monoidal. I want rigid, meaning in this context, it's not related with the formations of categories or these things. It's just that we have left and right duals for every object. I will also ask that the endomorphisms of one in this category. So here I will use this notation that I was using before. L and R here, this is associativity morphism, and these are just saying that the unit is really a unit for the tensor product. Just some isomorphisms, but what I will ask is that this is one-dimensional. I will ask that this is isomorphic to the field. And I have, okay, and here I will also ask for a grading. So I want to have a family of natural isomorphisms in C between all my objects, but in satisfying some nice conditions, the hexagon conditions or the grade equations, that will be braided. But in this case, I will ask that the braiding is symmetric, meaning that I want that the square of the braiding, when I compose the braiding 2 times, I just get identity. It's its own inverse. What I wanted to say that I didn't mention there, because it was the example, but here I have an abelian structure and monoidal. All the other things, and a braiding. I have 3 structures: a linear abelian, monoidal, and braidings. The other things that I'm requiring are properties of the category, but what I want is I want compatibility between my structures. So monoidal is hidden here. There is compatibility in this hexagon, which is the braid equation. It's how the tensor product of 2 objects braid with other objects, and is given in terms of the other things. But here I also want compatibility, so I will ask that the tensor product is bilinear in morphisms, okay? And because I'm in a rigid category, that will imply that my tensor product is exact, which is something that I usually want also, okay? So there are other examples of symmetric categories. One that maybe I will not give all the details, but is that if we have a Lie algebra, we could also look at the representation of the Lie algebra. And again, I always want, I will not want to write it because if I have underlying vector spaces, to have duals, I need finite dimensional. So when I'm thinking on modules or representations, I'm always thinking finite dimensional. And the idea is that we will be able also to get the monoidal structure because we can look at Maybe I will write a little bit, but it's super needed. But so here we have finite dimensional modules over the Lie algebra. And if I want to act in a tensor product, I will just write it in elements in these cases. I'm in the other case, I was acting with this diagonal thing that comes because this group element is a group like in a Hopf algebra. If you're thinking like this, here we have things that are more like primitive. So I will act in this other way. I will also have that K is a G module, but now the trivial action will be, or the action will be by 0 here. Notation. And then if I want to act on the dual, I will act way. And in this case, I will not write it, but again, the flip or swap is a map in the category of modules for the Lie algebra. So you can check, and that's a map in that category. It's an intertwiner. So we're fine. The flip works. It's a braid in this case, and because it's a flip, it's symmetric. Okay. There is another example that I want to mention just quickly because I will mention it a lot of times, which is the category of super vector spaces. Okay. This category, what I have are finite dimensional vector spaces that are graded by Z2. So my vector spaces will decompose in this way. And when I do the tensor product, I do somehow a convolution product. So if I want to know what is V tensor W as a vector space, it will be the tensor product. But what I'm giving extra, so here I have vector spaces underlying, but now it's the grading, the important extra structure. So in the 0 degree, I will have things that the coefficients give me 0. So we have 2 ways to do that. And for the one part, I will have things that coefficients give me 1 when I take them together, okay? I'm doing this example because in this case, we will get a grading that it's a little bit more interesting. Maybe I will not write everything else. Here, the unit will be the vector space, the one-dimensional vector space concentrated in degree 0, and you can write the dual. But what I want to say is the grading, because in this case, I will do the flip, but I will modify it by a sign that I will write -1 to the ij, where here I'm taking that V is in the homogeneous component VI. So that's the degree, 0 or 1, depending on which component you are, and W is in WJ. So it's a super in this sense. And this is very important. It's a very prototypical example, as it was also this other case. And I will tell you a little bit why. Let me see if I wanted to say something. Yes, I don't think so. Okay.
You don't require semi-simplicity?
For now, I'm not requiring semi-simplicity. I will care about semi-simple later. But yeah, this example will be semi-simple, but this example could not be semi-simple depending what I'm doing. And that's kind of, maybe I can make that comment now, since the question, that's a great question. I was going to say it later, so that's good. So this is semi-simple if and only if the characteristic doesn't divide the order of the group, so we can use Maschke's theorem here. Okay, maybe I want to say it's semi-simple if, I mean, it's not the only case, but I wanted to compare here with characteristic 0. And what happens in characteristic 0, when we are in symmetric actually, and if we are asking for some finiteness conditions that I will mention later, all our categories look very similar to this, or instead of representations of a group are super representations. So we have this set, I will mention this later, but this is the linear theorem. So kind of what happened is, okay, in characteristic zero, we understand under finiteness condition very well symmetric tensor categories, but what about characteristic P? That's kind of something, because here already in characteristic, okay, P, this category, and I'm writing this category, I know that it's just an example, I'm writing it because it will be important, is non-semisimple. This is already non-semisimple. And this will be one of our main interests. So maybe let me say one other definition. Because I will work most of the time with an special case, because I was saying something about finiteness. There are kind of finiteness that I will care about. To be honest, usually I work in categories that are finite, meaning that they have only finitely many simples, but here we can have a little bit more of liberty. But let me tell you what it's Pritanakian. So Pritanakian means just that it's a symmetric tensor category, as we defined before. But now we want that all the objects in my category have finite length, okay? And this already is good because it implies things about the home spaces, which were vector spaces, they will also be finite dimensionals in this case. So the length is, it's the length in the abelian category. So you have a Jordan-Helder series, and that's the length that I'm talking about. Okay, so we have that. And kind of what I wanted to mention as a motivation is this theorem that I was mentioning before there, just in words, but the Liñez theorem is that he has two papers, one in the early 90s and the other in the end of the 90s, right? So in that paper, he studied symmetric categories, in particular in characteristic zero, and he has a very nice result. So Pritanakian, so I do care about this finiteness, symmetric tensor categories. Okay, maybe I shouldn't write it again because it's in the definition, but okay. Pritanakian categories. And now we will need to ask for an extra condition, which is another finiteness condition that it's called moderate growth. Most of the time, instead of asking just for finite, people will look at moderate growth. Some people also study categories without moderate growth, but many people study this one. And it's related with how fast the length going. So what we will say is that for every object X in my category, for every X in C, there is some AX, real number, such that the length of the power of N, of the nth power of X is smaller or equal than the nth power of this constant. So there is a constant for each X, but there is some moderation in the growth of the length when I take powers. That's what I'm asking. In the case of finite, these things for free. Here, the linear cut, I told you that I'm algebraically closed fields, but it's important, it's very important here. Of characteristic zero. He described them, and what he says is that, no, maybe it's over K of characteristic zero. So any such category like this admits maybe any Pritanakian admits a unique, and I don't know if I defined this word before, I don't think so, but I can tell you later. A unique symmetric tensor functor from my category C, which many times we say that these category fibers when we have this property. And here, the natural host for this kind of fiber functors is S Beck in characteristic zero. Okay. So maybe let me say a couple of things. If the category, that's for people that study this, if the category C is symmetric fusion category means that I have semi-simplicity and finiteness of the category. So finite as a abelian category, so only finitely many simples and some other things that many are covered here already. In this case, the category C will be just what I was saying. These representations of the supergroups is the central element in the group of order almost 2. If I have order 1, it's just representations. If not, I will have something similar to the case of Superbeck happening in the braid. Now, if I drop semi-simplicity, but I keep finiteness, I have a very similar result, but will be representations of some special triangular Hopf algebra, which is coming from a group, but it's a symmetric product with some exterior algebra over some vector space, but I will also have this game with the element of order 2. So I will not write that one, but for fusion categories and for finite tensor, it's very well understood. It's very clear what happens. But when we go to characteristic P, this already is false. And that motivated a lot the study in characteristic P. So maybe let me write that, but I want to give you the example. So this is false in positive characteristic. And guess who is a counterexample to this? Who doesn't admit a fiber functor? Our favorite category that I didn't introduce yet, but Verp, Verlinde category doesn't admit fiber functors. So in a little bit, when I define them, I will tell you quickly why they don't. But maybe before I continue, let me motivate a little bit what we want to do. What we want to do. So there is a very similar result to this one of Verlinde that was proven characteristic P using a different host for these fiber functors. And people think that Britanakian categories of moderate growth is a good place to do commutative algebra and algebraic geometry. And for that, we want to define and develop theory of certain kind of algebraic structures on that kind of categories. We have done a lot in Beck. We want to do it in that kind of categories, and that categories, or one example, and a very important example is Verlinde. That's the idea. So maybe tell you Verlinde category. Let me tell you Verlinde category, and I will tell you more or less the theorem that I want. That it's not mine, that one. It's about similar for than the linear, but in characteristic P. So here.
I think the participant has a question.
I'm sorry, yes.
Do you know if in general in Deline's theorem you get like that the functor is full or faithful or anything like that?
Some of the things are well behaved, but faithful, it's usually not well behaved. In general, this, when I ask, I mean, depending which version you look, but when I ask, and I didn't say that at the end, when you define what symmetric tensor functor is, you want a k-linear functor that behaves nice with everything in the abelian category, with the monoidal product that behaves well with the symmetric braid, but you don't ask that the functor is faithful. Exact. And when you are, exact. And when you are working with k-linear monoidal categories, exact and faithful are the same. So you will see that in a little bit when I give you an example, the one in characteristic P will fail faithfully, and it's easy to see. So I want to define finally Verp. There are a couple of ways to define this Verlinde category. For that, I want to use this example, the example that we saw. before rep set P, this is a non-semi-simple category. So what we want to do now is we want to construct a semi-simple category from a non-semi-simple category. So there is a process called semi-simplification. There is a nice paper by, I think, of an Nostrict about this. This is a particular case of a more general construction that it's taking some quotient of your category, but I will work in this specific case. Hopefully, in a little bit, I will define our category. I'll mention some things about it. So, in general, if I'm working with one of these symmetric tensor categories, I could take a tensor ideal and use that to create a new category. So what I will do is I will keep my same objects, but I will quotient at the level of morphisms. In this case, I want to do a specific example. So what I will say is, okay, maybe let me write. I will be working, see, a symmetric tensor category. In general, to be able to do what I'm about to do, I need a spherical, or I need to take traces. But okay. So what I want to do is the following. I want to define, if I have f from x to y, morphism in C, I will say that this object is called negligible if when I compose this morphism with any, or maybe pre-compose this morphism with any other morphism that now goes in the opposite direction, or any other, yes. Okay. If for any G that goes in the opposite direction, when I take the trace of the composition of these two, I get 0. And what I mean is that I will be able to somehow discard these things. So I will define the bar as the category with same objects than C, and the home space in my category, in my new category, is given by the quotient between the original home space and these negligible morphisms. Okay. I will write, sorry, I didn't put the notation, that's bad, but I will say that N, X, Y is the collection of the negligible objects. I don't have to write it. What one could ask is what things are inherent, right? Because I started with a nice category that was monoidal, abelian, symmetric, and all that. And basically what happens is that all that things are respected when we take this semi-simplification process. So this C bar has all the things that we like. So I doing this process, maybe behaves well, is compatible with all our structures. And moreover, now this is semi-simple. That's this is semi-simple symmetric tensor category, and we have this semi-simplification functor that goes from C to C bar. This functor is quite well behaved. It's monoidal, it's symmetric, but it's not exact in any of the sides. So this is symmetric monoidal. So not only behaves well with the tensor product, but also with the grading, K-linear, but not exact. And later I will show you more or less easily why it's not exact by showing that it's not faithful in one example. So what we will do to, let me see if I can put it in something, I think it's fine. So what I will do is I will semi-simplify my category that we had before. And I want to say that actually the Verlinde category, maybe I can do this, can be constructed in many ways, as I said before, but there are two ways that we will be interested in. So maybe let me say a little bit more about that. So Verlinde will be the semi-simplification of this sheet, and also can be obtained as the semi-simplification of the following category. So who will be alpha t for me, will be the polynomial algebra but truncated. So I'm doing this. And I want to mention both because first of all, the other one is a more clear, it's clear, maybe both are clear easily, but in this one we were talking about the symmetric thing and it's clear that it's symmetric and everything, but this is the approach that we use to construct actually the Lie algebras, and also Canan, who he's a graduate student, I think finishing soon in MIT, he also did this kind of computations, and using this Hof algebra, it's a very useful perspective to construct the things. How much time I have? 20 minutes or to decide what I will say? 20? Okay. Okay. So maybe let me tell you a little bit about this category so we get more familiar. I will erase this. I just wanted to mention this other one because I will be using it later, but so something that I didn't say in general, and I could have said before erasing this, is I told you that it's semi-simple, so it's natural to want to know who are the simples in my new category. The simples in my new category come from indecomposables in the original category, which had dimension 0. So the trace of the identity was 0 in that category. So what happened when I semi-simplify that I erase it is that I told you we keep the objects, but we were cutting the we were quotienting the morphisms. So now what we got were isomorphisms. So things that were in the composable now are 0. Or that were non-zero now are 0, or isomorphic to 0, and that's what happened. So the isomorphism classes of indecomposables. And here I will be talking about the category here, which is the representations of this Romanian kernel that we were looking of the deep group scheme. So that's isomorphism classes of the indecomposables are represented by the nilpotent Jordan blocks of different size. Okay, so we will go up to p minus 1. Yeah. Here I'm writing it's p. I want to mention who is p. So here I mean characteristic p, right? So are the nilpotent blocks, I will call them Li here. Later, I probably will abuse of notation and will use the Li also for the image in the quotient, and these are of size I. So we have a very nice, I mean, I will not go much in detail in this, but we have a nice description of this. We have the cyclic basis to describe this, and that's useful. I will not do that, but I wanted to mention that It's okay. One thing that I wanted to mention is that these in the composables are self-dual, that you can also look at how the fusion rules or the tensor product works, and you can decompose it. Maybe let me say that L1 is the monoidal unit. And for example, let me say what happened when I do this one. This one give me PLP. I'm mentioning this case because it's kind of the ones that I will care, but now when I go to the semi-simplification, a lot of the times I will use double S for semi-simple, and sometimes now I use it for also semi-simplification. I hope it's understandable. What happened? I told you who are the indecomposables, but now to know who are the simplest in my new category in this simplification, which is Verp or Verp P, only survives the one that have dimension different from 0 in this field. So the one that will die is this one. It's LP. LP now is 0. So now I will abuse of notation as I told you. So maybe let me say LP is 0 in Verp P. L1 still the unit. The unit. Now I didn't want to erase that. Okay, I will erase it because anyway, it doesn't say anything that much. Just so that we can also look at it in the other way. Okay, but what is nice, it's how are the fusion rules described here. Lij, and it's like a Clebsch formula, and it's a truncated Verlinde formula. So what we will do, we will sum the k between 1 and the minimum between many things, I, j, p minus I, p minus j, and I will be summing all the else in which I take the difference between ij and get the part, and qk plus 1. Let me double check it. No, of course, it's too small. Yeah, like this. So maybe it's not very worth to do many of them. I mean, I could do some examples. I don't know if it's very important, but some remarks. I mean, it is important in the sense that you get familiar, but for some reason, maybe I will skip it. I was doing some of these fusion rules. Some remarks are, okay, we know that this is the unit, so we generate just the category of vector spaces. But now, we could also consider L1 and LP minus 1. And what this generates is the subcategory. And this subcategory is equivalent as symmetric categories to the category of supervector spaces. So inside Verp, I have always supervector spaces. That's nice. Moreover, so this is inside Verp. Actually, my category has another nice subcategory, which I will call Verp plus, and it's given by the odd.
But this L1 to the RP is 0, right? So it's kind of,
No.
or no? So because according to this formula, right? So you take L1 tensor.
When you take L1 tensor L1, you should get L1.
Oh, sorry. Never mind, sorry, yeah.
It's because a lot of these things
Yeah,
get,
yeah, sorry, never mind.
you pick the smallest and it's a 1.
Yeah, sorry, yeah.
No, it's okay. Yeah, it's confusing because of all this minimum, but that's why I was going to do the example, but I don't have much time, so I wanted to get to the other thing. But yeah, L1 is a unit, P minus 1 squares to the unit when you do it. Also because here you get the 1 and it's short, the formula. What I was saying is that if you take the odd labels, this is also a tensor subcategory. And actually your Verlinde category factorized as S-vec, the linear product, so it's like a direct product, Verp plus. So for many things you care about Verp plus at the end of the day, because, but not for what we were doing. For what we were doing, it's useful to have super vector spaces because you could project to super vector spaces and recover Lie algebras or super Lie algebras. Here, I wanted to mention before forgetting this question related to faithfulness and all that. So the semi-simplification thing in this case will go from rep alpha p to Verp p. But here we will see that it's not faithful because we know that it sends in the composable LP to 0. Okay, so that's already bad. And maybe let me do, or right, I will not do it, but I just wanted to tell you that Verp doesn't fit, or Verp doesn't fit in this kind. So Verp doesn't admit let me say it like this. There is not a fiber functor in that sense, in the sense that I have this symmetric tensor functor from Verp to S-vec, which was the case in positive characteristics. So the linear theorem really fails in positive characteristic. In characteristic 0, every symmetric category that it's good enough, this one is finite, so it's of moderate growth, like that one's fiber to S-vec. In this case, cannot, in particular because here we're in vector spaces. So we have a notion of dimension that it's called the Frobenius-Perron dimension and comes when you look at the Grothendieck ring. You can look at the maximal eigenvalue of left multiplication by the objects. And in these categories, they coincide with the dimension as vector spaces. So they are always integers. Whereas in general, they could be real, but in symmetric, in characteristic, or characteristic 0, or in super vector space in particular, in any characteristic. But here, when you do, for example, p equal 5, so let's say that I'm in p equal 5, and I do this, I want to double check, but I think I wrote it correctly. I get these fusion rules. So if you compute the dimension, which it behaves nicely, it's multiplicative and additive, and this one is the 1 because it's a unit, you get the golden radius. So it cannot map. Yes.
And here does the Frobenius-Perron dimension match up with like the trace dimension and the other dimensions, or?
No, in general, no. Depending the category. I mean, this one maybe because it's quite nice, it's symmetric. So maybe they match, but in principle, no. I don't think so. Okay. In general, no. Maybe for these categories that are nice, yes. But since this dimension can never, so if we had a fiber functor, this L3 should be mapped to something and it will not be an integer. And actually, a comment is that this category is tensor generated by one object. It doesn't matter now. And I will go to the algebra part. I will not get there. But maybe let me just say one last thing, given that I left this here. There is something in characteristic P, positive. There is a generalization of the linear, or a version of the linear theorem in characteristic P. Ostrich proved a while ago a theorem like this for the fusion case. So meaning that I have semi-simple, which is asking more. And the theorem in that case is that a symmetric fusion category or a pre-Tanakian symmetric fusion category always in characteristic P fibers to Verp P. That's why Verp P are important in part, one of the things, but they are the natural host now. Now, and Colombier, Ettinghoff, and Ostrich, they generalize this. So instead of fusion, they not require fusion, they require other thing, which is technical, but people think that it's always true that it's something called exact Frobenius. So it doesn't matter that much, but I wanted to say there is kind of an analogous, and people think that this is a really important example to understand. So now I don't have that much time, so let me pick very quickly what to say. So one thing that I wanted to say is that, and you are much more expert than me in all this, but finite dimensional Lie superalgebras in characteristic zero were quite well understood by in the 70s that Kac studied this special class, the contragredient Lie algebras that are also called Lie algebras associated to a matrix. So you have this Cartan matrix are related to Kac-Moody, but in principle, they could be a little bit more general. But in characteristic P, this is already more complicated. There is also work on this in 2010, more or less. And there are some classification results and many cases in lower characteristic needed to be done by hand. And some of the things is that using these Verlinde categories, people was able to recover that exceptional cases using magic squares or super magic square, El Duque and some other co-authors. And also Cannon use this idea of semi-simplifying things. And then, for example, if you are in, maybe I didn't write this, but if you are in P3, in P equal 3, Verlinde in that case is super vector space. So when you play there the game, so when you go from this thing here, and you semi-simplify, you land in supervector. So you get super algebras in characteristic 3, which was one of the hard cases. In principle, maybe we have to run, so maybe I will pick my theorem now. Okay, I didn't plan that well how much I wanted to say. Sorry, but I will not take that long. Sorry, I will pick what to say. So maybe just let me say things. Okay, so this theorem of Kac is just that if we have this A, right, and a matrix, there is some set graded Lie algebra such that it has a lot of nice properties. I mean, maybe I will not write all the properties, I will mention some, but one of the nice properties that we like it when we were looking at this and we were trying to do this in Verp was looking at it has a triangular decomposition. This, I mean, it's very similar to what we saw in the first talk today, right? We have the EIs generating this in degree 1, the FIs generating this in degree -1, and this is the degree 0. So I will not write that, but H is an abelian subalgebra of degree 0. This is generated in degree 1 by certain EIs that are these Chevalier generators that I mentioned, and the FIs generating degree -1 here. And we have the usual relations that I will not write, are similar to what Alan wrote before. So I will not write that. That's a lot of the points that I have here, but other thing that has, so plus conditions. The other point that I have here is that, I will not write it, but it's kind of universal. Every other Lie algebra that satisfies this, it's subject to ours. So what we proved is that, maybe let me just say that, and maybe one other thing, I'm saying why this is important, but what we prove is that if we started with a Lie algebra in this category, and that's the key point, so our result here if G, and I will need to write this, it's a Lie algebra. And is a derivation of order P, we can get or we can semi-simplify. I mean, here this should be, sorry, this is a contragradient, maybe. So I have all this information from the matrix. Then we can get Lie algebras in Verp by semi-simplifying our Lie algebra. Yeah, so it's easier. We needed the derivation of degree P because what we do is we endowed this Lie algebra. So we start looking at modules over that, and to look at modules over that, we need to act in some way, and we act with that derivation of degree P. So I'm rushing in this part. It's a little delicate, the definition of Lie algebra in Verlinde categories or in other categories. I mean, in Supervec, you still have elements when you want to define what would be. And this is the theorem, just the simplification. We have another theorem. So semi-simplification on contragradient Lie algebras give you some Lie algebras in Verlinde categories, basically, but we want to know if we have a notion of contragradient, of root systems, and all the nice things that in this case happen, but we want to know if we have a general notion for that. So what we did was that we defined and we proved some cases in which this exists, contragradient Lie algebras in Verp V. To do that, it's a little delicate because many of the things that you can do or you can think about, you think it with elements. And when you're in categories, you don't have elements anymore. In these categories, Verp, you cannot think of the elements that easily. And also the definition of Lie algebra has some some subtle points. Sorry, I cannot pronounce that word. And just, I will end with this, but in Supervec, when you're thinking of Lie algebras, you need to ask, you will have some form, which is your bracket, right? And you need to ask for the condition that X tensor X goes to 0. When you are in characteristic 2. When you go more, in characteristic 3, you need to also look for something like this. And this is an extra condition that in principle people was not looking at the beginning when they defined the algebras in the symmetric categories, and the netting of defining this notion of this extra condition. It's a condition in degree P that you need in characteristic P, basically, to be satisfied, to be really to capture what you want. Otherwise, he used the notion of operatic Lie algebras, which is what people was using before. But yeah, sorry, I have to rush at the end, but the idea is that we are able to construct some new examples. And with that, you can construct group schemes in Verp P also using Venkatesh's previous result. So thank you.
Any questions for the speaker?
You can do the Verlinde in the quantum case, and their quantum motion currency is 0. Yeah.
But it could be good to think, yes. We actually, what we would like to think, it's, that there is this quantum groups, and then people think of a generalization of quantum groups, these Nichols algebras, which also have root systems and Weil-groupoid and things like this. So that's our goal, to define that. To do it in VEC, you need the Jeter-Drinfeld models and that thing. So we should study some more things in Verlinde. So many things we don't know yet in Verlinde categories. For example, the Drinfeld double that someone was mentioning, or that maybe I was mentioning the first talk, the Drinfeld center of the Verp, we don't know it yet. We're working on that, but we don't know it, and we kind of need that kind of thing. But I didn't think on the quantum version.